We've looked at gases. That was our last topic. Now we're going to look at acids and bases. And in fact, we're going to have to dip a little bit. This is chapter 16. We're going to have to dip our toes a little bit in chapter 17. So for some of the topics, and I'll relate to you when those occur, so you can do some reading on chapter 17. But it's just enough of chapter 17 so that we can understand acids and bases better. All right. So as usual, I have a table of contents, but we're going to hit those topics anyway, so we're not going to stop here. But first, we do want to look at chapter 17. I need to introduce some concepts relative to equilibrium. And understanding equilibrium will immensely help in grasping some of the concepts of acids and bases. So, what do we mean by equilibrium? Well, look at the word. Equilibrium, the first part of it is equal. Something is equal. And in fact, in order to describe equilibrium, we have to understand that two opposing processes are occurring at the same time, but there, at some point, those processes are equal but opposite in direction. Our example here is evaporation and condensation. If you have a liquid in a closed vessel, when you first put it in, there are no molecules from the liquid in that headspace above. But if we keep it closed, then evaporation takes place. Some of those molecules in the liquid will migrate, so to speak, into the headspace and become gases. And after they reach a certain point, some of them start returning to the liquid phase. So you get this exchange between liquid and gas. In the beginning, it's all evaporation. The liquid just goes into the gas phase, and as you get more and more of the molecules in the gas phase, then you have a higher probability of some of them returning, and that's condensation. So at some point, you get an establish an equal rate of evaporation and condensation. At that point, we say we have an equilibrium established. Now, on the surface, from outside, you don't see anything. I mean, you might see initially a decrease in volume of the liquid as some of it becomes gas, but that's all you notice. It's the microscopic activity that's really the interesting part, because the activity, evaporation and condensation, those two activities taken together are occurring at furious rates. Just on the microscopic level, it's unimaginable speed. But at the macroscopic level, looks like nothing's happening. Okay, so that's what we see here. The volume's decreasing and we get more and more and more gas phase molecules from our liquid. Now, how many of these go into the gas phase? Right? It depends on the nature of the liquid. Right? For some liquids we call volatile, a large amount of the liquid will become gas before an equilibrium is established. But for some liquids, you get virtually none. For instance, mercury. Mercury is a liquid metal. The headspace above mercury is virtually devoid of mercury molecules, mercury atoms. But something like diethyl ether in this environment will decrease dramatically in volume and put a large amount of the liquid molecules into the gas phase. And you can measure that difference. There's a pressure up here that builds up in a closed vessel above that liquid. We call it the vapor pressure. And for the more volatile liquids, you get a higher vapor pressure. Okay. So that's a description of equilibrium. Now we want to think of equilibrium in terms of the chemical reaction. When we write a chemical reaction in generic form, we used to write it this way, right? Reactants yield products. And we're saying that the reaction goes that way. And that's all there is to it. But the fact of the matter is, most, if not all, reactions can go both directions. You can get reactants going to products, and you can get products coming back to reactants. So now we're setting ourselves up for a two-way traffic. Just like our evaporation and condensation, you can go to the right, you can also go to the left. Now, how much goes this way and how much goes this way in their competition is dependent upon the nature of the reactants and products and how they behave with one another in this description of our balanced equation. Some of them like to go mostly all over here. So for all intents and purposes, this reaction only goes one way. And some of them prefer to go this way. So most of it is reactants and very little of it product. But there comes a point where the rate this direction equals the rate this direction, forward and backwards. At that point, we have equilibrium. Now, all of this occurs under specific conditions. We have to describe primarily temperature, but also if there are any gases involved, we describe the conditions in terms of pressure. And then concentration of the reactants and products also enters in. So in this equation, that square is supposed to be a double barbed arrow. Something went wrong with the programming. But if let me write it up here the way it's supposed to be. So we've got a reaction here we described as water, which is a gas, plus carbon monoxide, which is a gas. And it can yield hydrogen, which is also a gas, and carbon dioxide. Okay. Now, first of all, is that balanced? That's the first question that enters my mind after I know what the reactants and products are. Is the equation balanced? Well, let's see. Two hydrogens, two hydrogens. One carbon, one carbon. Two oxygens, two oxygens. We're balanced. Okay, now we can talk about what would happen if this equation described an equilibrium situation. In other words, the reaction has already occurred to such a point that we have some products and some reactants, and now the rates, the opposing rates are balanced, they're equal. Okay, now at this point, what if we change something? What if we add more water to the flask? As a gas, of course. If you add more water, what's that going to do? Well, now this reactant encounters more of these reactants than it did before. So the chances of reacting to go that direction have increased simply because you have more of these available and the chance encounters between these two molecules increases. So when that happens, you tend to push this rate toward products. And that's exactly what happens. If you add water here, you're going to get the reaction to shift that way until the rates are balanced once more. Okay. What if you add more hydrogen to the flask instead? We're at equilibrium again. We have more hydrogen. The same scenario, the same description is valid here. You have more of these, and there in any of these carbon dioxide molecules encounter more hydrogen molecules. So the chances of having a return reaction increase. And that's what happens. You get a shift this direction until we reestablish balanced rates. Okay. And let's see. Here we go. There is a quantitative expression for this equilibrium. And this is a good way to write it. If we have reactants here, A and B, and yields C and D products, okay, and this is the coefficient for A, this is the coefficient for B, coefficient for C, and coefficient for D. Okay. We can write an expression that yields a constant value. That's the K. This is known as the equilibrium constant. That equilibrium constant can be written this way. If we know the concentrations of our products and our reactants at equilibrium, once equilibrium is established, we can measure the concentrations, not the total amount, the concentrations. Then if we put the products in the numerator times one another, and we use the coefficients as the power. And then in the denominator, we put a similar expression for the reactants. Using the coefficients as powers of those concentrations. If we write it that way, then at a given temperature, this value is constant. So now, if we change one of these factors, then the rest of them are going to change in order to maintain that constant value. So say if we increase C, then we're going to have to create more A and B in order to shift that relationship, maintain that constant value. That's the equilibrium constant. Now, sometimes these equilibrium constants have subscripts, just so they give us some more information about what are they describing. Sometimes we'll put an EQ here, just as a general equilibrium constant. Sometimes we'll put a P there, which means equilibrium constant with pressure. So if they're gases, then these concentrations will be expressed in partial pressures of the gases in, say, atmospheres, rather than concentrations like molarity. Or the one that we're going to study in a minute, so we need to do that. The one we're going to look at in just a few minutes is Ka, equilibrium constant for an acid. And I'll have to describe what that means. But you can have different subscripts here and they mean different things. Okay. So here's an example of a K value for this reaction, right? The Haber-Bosch process, where we take a nitrogen gas and combine it with hydrogen gas and make ammonia. And then if we write the equilibrium expression, we have the product concentration, and we use square brackets. Square brackets are understood to mean the concentration at equilibrium. So the concentration of ammonia to the second power, because that's the coefficient of ammonia, divided by the product of these two values, nitrogen to the first power times hydrogen to the third power, its coefficient. Okay, that's our equilibrium expression for this reaction. Okay, let's see. There's also one other convention that needs to be mentioned. And let me write a different equation here to illustrate. Say we want to take that solid, potassium chlorate, and we want to add some heat. And we use a symbol, we use a delta symbol. That means add heat. And what we get is potassium chloride, solid, plus oxygen gas. Right? Now I need to balance this equation, correct? So let's see. We've got 3 of these here, and I need, how about if we do 3 here, and 2 here, and 2 there? I think that should work. 6 oxygen, 2 potassium, 2 chlorines, we're balanced. Okay, now, how would we write the equilibrium expression for this one? Well, up to now, you would assume that the convention says the equilibrium expression would be this. We'd have this one squared times this one cubed divided by this one squared. Okay? Here's the problem. During this reaction, does the concentration of that one change? No. It's a solid, and it's there as a solid until it's all gone. We have no expression for its concentration. We can talk about its density, yeah, but density doesn't enter into this calculation, only the concentration. So this concentration doesn't change, and that concentration doesn't change. You get more of it, but expressed as terms of molarity or any other form, it doesn't change. So we don't include solids in our expression. Okay, so the expression is only oxygen. That's it. The equilibrium is based upon oxygen only. Now, the same holds true for pure liquids as well. There's one reaction where we can produce mercury. We won't talk about it right now, but it comes out as a liquid. That's not part of the equilibrium expression for that reaction. Or if we have a reaction that produces pure water, that one is also excluded from the expression. So solids and pure liquids are not considered in equilibrium expressions. So for our purposes, we only include gases and aqueous components that can be expressed in terms of some concentration unit, usually molarity. Okay. So I want to draw attention to one other thing. The difference between the equilibrium constant, which is a constant at a given temperature, doesn't change, and that versus equilibrium position. Equilibrium position, equilibrium constant, does not change if we change the concentration of reactants or products. But the equilibrium position can change. If we if we add more of a product at equilibrium, then it's going to shift toward reactants. Right? That's a shift in position because now we have different concentrations for reactants and products. Even though we used up some of that added product, we didn't use all of it up. We only used enough of it so the equilibrium could be reestablished. And the K value is constant. The K did not change, but we have different concentrations now of reactants and products. And when you put those together in that equilibrium expression, you still get the constant. Okay? So that's the difference between the constant and the position. The position can change even though the temperature doesn't change. All right. So we're going to start to segue into acids and bases. And perhaps this slide should have been introduced a little bit later because we haven't defined for you what an acid and a base is. So maybe what I'll do is skip this one and come back to it once we've defined our terms. Let's see. Yeah, I think we'll come back to that after we talk about acids and bases in detail. Then we'll come back to some more equilibrium discussion. Okay, so to define an acid. Well, we're going to take this historically speaking. What was the first scientific explanation for what an acid and a base happened to be? And that was proposed by Arrhenius. He said that acids were any compound that contained within the molecule a hydrogen atom that could be separated. Once we put it in solution, aqueous solution in particular, that hydrogen atom, ion, would separate from the molecule. So it would produce now a hydrogen ion and some leftover anion. A base, so we write it generically like this. There's your hydrogen, your proton, right? And there's the rest of the molecule. So why do I call it a proton? Well, when it separates like this, that charges balance, negative, positive, neutral. What is a hydrogen ion, H+? Well, think about it. If you got a proton here and an electron out here in this space, if you take the electron away, what do you got left? A proton. Now, for most isotopes of hydrogen, that's true. We're not talking about the rarer deuterium and tritium molecules where you have a neutron in here or maybe two neutrons. Most of the time it's a proton. So when I say proton, I'm talking hydrogen ion. Okay. So this is an Arrhenius definition of an acid. Okay. The molecule dissociates and produces a hydrogen ion. His definition of a base is some component here attached to a hydroxyl. Remember the polyatomic ion, OH minus, hydroxyl. And when it dissociates, it produces this positive plus a negative. Okay? That was Arrhenius' definition. So the base must have a hydroxyl in its makeup that can be dissociated. Now, acids and bases have characteristics that can be qualitatively described. Acids taste sour, bases taste bitter. That's why most medications that you receive, particularly antibiotics and some others, if a little bit gets on your tongue, say the capsule breaks or the tablet dissolves too soon, you'll get a bitter taste because the active ingredient in that capsule, in that drug, is a base, and it produces a bitter taste. Also, bases, if you get some on your fingers, feel slick. Now, we don't do those tests anymore, typically, because it's just not a good idea to taste your chemicals. Right? They might be hazardous. But we have some foods that are this way. Vinegar is an acid, and it tastes sour. So when you bite into a sour dill pickle, that's what you're getting. You're getting lots of vinegar on your tongue. Okay, this was Arrhenius' definition of acid and base. But there's a problem. What would happen, or what did happen, when, and let's see, this occurred in, this Arrhenius definition was 1884, right? The end of the 19th century. But what was discovered by other scientists was you could get basic effects, and they could measure, roughly speaking, they could measure acid versus base with color indicators. Litmus was one of them, phenolphthalein, various colored dyes can tell you if you have an acid or a base. The problem arose with some molecules that did not have a hydroxyl in their molecular makeup, but they produced the base effect. For instance, ammonia. If we dissolve ammonia in water and then test it, it produces a base reaction. So where's the hydroxyl? There's no hydroxyl there. It wasn't until we understood what was happening in aqueous solutions, when this molecule was dissolved in water, it was reacting with water molecules. Okay? And it was producing this compound. Okay? That's balanced. One hydrogen goes here, the other hydrogen stays there, and now you have a hydroxyl. And in aqueous solution, this dissociates. Into these two. Now you can match this to Arrhenius' definition, but there's no direct correlation here because ammonia does not possess a hydroxyl. It's only with the reaction with water. So we needed a new definition. And along comes two chemists, Bronsted and Lowry, independently proposed this. So they're both given credit. The Bronsted and Lowry definition focuses on only the hydrogen ion. Okay? They figured if there's no hydroxyl in the molecule, why bother with the hydroxyl in the definition? Just focus on the hydrogen ions. And it works. So in this case, if we focus on the hydrogen ions, a Bronsted-Lowry acid donates a proton in a reaction. So who's the donor here? One of these hydrogens is transferred over here. This is the donor. So this is the acid. And this is the Bronsted-Lowry base, which accepts the proton. Okay? That's the Bronsted-Lowry definition. Here's another example. If you put hydrogen chloride gas, dissolve it in water, it also reacts with water. And the HCl donates a proton to water, so HCl now is the acid. Water becomes the base. That's interesting, isn't it? In this reaction, water is an acid, according to Bronsted-Lowry. But in that reaction, water is a base. It accepts the proton. And now what you have is what's left over. The chloride ion is the anion left over after the transfer of this hydrogen to water. Now we have this new species. We call that the hydronium ion. And in fact, in aqueous solution, these acid-base reactions occurring never produces independent protons just moving around. Right? It doesn't happen. Those protons attach themselves to water molecules. So they always, in reality, they produce hydronium ions. But for convenience sake and for calculations, it works just fine. Sometimes we will write it like this. Okay, we just leave the water out, recognizing that there is water there. But it simplifies calculations if we write it this way. This is just a simplified convention. It's not reality. Reality is transfer of proton from one place to another. Okay? So this, in general, is what happens with an acid in water. We transfer a proton from the acid to the water molecule, and that produces this species. Okay? Now, the naming convention is the one that transfers, the origin of the proton is the acid, and the receiver is the base. And then on the product side of the equation, this base is correlated with a conjugate acid. Now, this has an extra proton that it can donate. So it's the conjugate acid of the base. And conversely, this acid produces a conjugate base. Now that that conjugate base is missing a proton, perhaps it will accept the proton in return. So, to make a long story short, this reaction is in equilibrium, right? There's that concept again. The forward reaction is balanced by the reverse reaction. Okay. This is the artist's concept of what happens, right? Water molecule has these extra lone pair electrons sticking out on the outside. And this hydrogen, separating from the chloride, the hydrogen now is missing electrons. So it bonds to this water molecule, and the bonding, right? 2 electrons equals a bond. So when it attaches itself, it forms this bond, and now we only have 1 lone pair. But we also have a positive charge because this over here, the hydrogen ion is positively charged, and we have to balance the charges. So now this hydronium ion is positively charged, and the chloride retains the electrons. Okay. So let's see if we understand what happens during an acid reaction. When we're creating an acid and we're producing a conjugate base from the acid. Notice that when the reaction occurs, let's see, I didn't write it completely. So let's change this and write it the way it actually happens. There we go. There's our acid. There's its conjugate base. There's our base. There's our conjugate acid. Notice what we're saying here. Only one proton is transferred in a reaction. If you transfer more than one proton, then you may be describing an overall reaction, but you're not describing an acid-base reaction that produces conjugate acid, conjugate base. So to simplify that, the conjugate base of this acid is absent, one proton only. Okay, in this case, that's easy because it only has one proton. But some acids have more than one proton. For instance, let's see, sulfuric acid. Okay. Transfer one proton. That leaves HSO4 minus, and that proton transfers over to water, makes a hydronium. Okay. Notice I only transferred one proton. That's the way we do it in acid-base reactions. Only one proton at a time. So this acid produces that conjugate base. Okay, one proton at a time. Plus, notice that this part of the reactant has to be present here and here. So the one hydrogen left over plus the sulfate constitutes the A minus of our generic equation. So with that in mind, which one of these are conjugate acid-base pairs? Not that one. That first one, those are two intact acids. So that's not going to work. How about this one? If you remove a proton from a hydronium as the acid, what do you get? You get water. You don't get hydroxyl. So this is not an acid-base pair. How about this one? Sulfuric acid. We transferred two protons to end up with sulfate, so that's not an acid-base pair. HCN, remove one proton, you get a CN minus. That is an acid paired with its conjugate base. This one is true. Okay. All right. Now, let's go back. Let's go back to our equilibrium discussion. Now that we know what an acid and a base both are, let's go back to our equilibrium and discuss acid reaction in terms of equilibrium expression. Okay, let me see. Let me go back until, let's see, that we didn't go that far. Here we go. Okay, so here we have acetic acid, HC2H3O2. This is an aqueous solution, and I'm going to use a simplified expression here. Not the hydronium ion, but we're going to say that the hydrogen ions are free. When we know they're not, but the calculation becomes easier if we just leave the water out of it for now. In this equilibrium, we dissociate a proton in aqueous solution, and we're left with the acetate polyatomic ion. Okay, that expression, this is aqueous solution, aqueous, aqueous. All of those can be expressed in terms of molarity, concentrations. So we keep all of those in our equilibrium expression. So the K for that would be written this way. Products to the first power. This is balanced equation, by the way. Then the acetate ion, those products, and then the acetic acid molecule and its concentration. Okay, so if we know the concentrations of each one of these, we can calculate the Ka, the acid dissociation equilibrium constant. So which one of these qualifies? Well, I think this one probably does. Okay? All right. So let's take this one as an example also. Now, this is not an acid. N2O4 becomes, this is a gas, decomposes to 2NO2s as gases. So our equilibrium expression here, notice that our concentrations that are given for this calculation are in molarity. So we write a standard equilibrium expression. The K here is NO2 squared divided by N2O4 to the first power. Now we're given equilibrium concentrations of each one. So in the numerator, we have 0.060 molar squared. And then in the denominator, we have 0.055 molar. Okay? Now, if we square this number and then divide it by that number, we get our equilibrium constant, which should be 0.065, 0.065. Okay? Notice anything unusual about that number? There are no units. We did not put units here. Now, to be sure, you can calculate units. Use molarity squared divided by molarity is equal to molar. So the actual units, if we calculated them, would be molar. But that could be confusing. If we just saw that number, we'd think, oh, that's the concentration of something. No, in this case, it's the equilibrium constant. That, in addition to the fact that these coefficients could be anything. They could be 2, 5, 7, 25. You could get some really strange units out of these calculations. And every equilibrium constant will have a different unit of measure. So, by convention, we never write. We never write the units. We just be very careful that we set it up correctly and we do our calculations correctly. So we have to take extra care there. We can't use the units to guide the operation. And in any standard manual of values for equilibrium constants, you'll see that they will not have units given. What they will do is say the equilibrium constant in this table of calculations of different reactions, how is it derived? Is it based upon molarity? Okay, that's good. Or is it based upon partial pressures of gases? Or is it a combination? Because you can have aqueous solutions that produce gases, and in that case, you'll have a mix of the two. So you need to know that in advance. And as long as you're given that information, then the calculation, if done correctly, will give you, say, we wanted to go backwards. So we knew this, and we know that one, but we don't know this one. So we can solve for an unknown. If we have the correct units in there, and we know what they are in advance, then our answer will come out in molarity in this case. Okay. We can say something about the reaction in general by looking at the magnitude of the K value. If the K value is much larger than 1, what does that mean? Well, look at it in these terms. If it's greater than 1, I mean much larger than 1, that means this part of the equation must be very large in relation to that one. Right? If it was the other way around, it'd be a lot less than 1. Right? If this is very small and that's very large, you get a fraction that's less than 1. If it's greater than 1, we're saying that the reaction prefers at equilibrium to be mostly product. Vice versa, if the K value is much less than 1, we're saying that the reaction at equilibrium prefers to be reactants. Okay? All right. So in addition to that, I'd like to say, if we say the reaction is greater than 1, the K is greater than 1 for a given reaction, that means it prefers product. But if we look at it in reverse, if we just take the reaction and flip it around, now the K is going to be still favoring the same species, but now they're in the reactant position. So what do we do with the K? Well, if we flip the reaction, that means this goes on top and that goes on the bottom. So you're actually taking the inverse of that value, right? If you take 1 divided by that number, then it would give you the equilibrium constant for the reverse reaction. All right. This just states the obvious. If you have an equilibrium constant, you know the balanced equation, you can write the expression for the equilibrium constant, and you have all concentrations at equilibrium are known except for 1, then you can solve for it. Just like any algebraic expression, if you have 1 unknown, you can solve for it. Okay, so if the equilibrium lies to the right, the value of K is greater than 1. And if the equilibrium lies to the left, the K will be less than 1. Now, we can't say that a perfect balance between reactants and products equals a K of 1. And the reason we can't say that is because of these coefficient powers. They kind of really mess with where the middle ground is. So we have to say much larger than 1 or much less than 1. Then we're pretty safe in those regions. Okay, let's go back to where we left off. Let's see, finish talking about acids and bases in particular. Okay, right. We identified the proper definition and identification of an acid conjugate base pair. 1 proton transfers, and you have the A- left over. This one qualifies. Okay, the others don't. Okay, now what do we mean by a strong acid? And when I say strong acid, I'm talking about strength in chemical terms. If we talk about, well, a common misconception about strength of an acid is based upon whether it can do damage, right? OSHA or EPA rules say an acid or a base is corrosive. That is, it can damage materials, it can damage your skin. If it produces a pH in aqueous solution of less than 2 or greater than, so I'm scratching my head, greater than 10.5, I believe. So more basic or more acid, either one. Now, I haven't even defined pH yet. All right, so there's my chance. I'll get to that in a second. In other words, it has to be that definition of strength is not the chemical definition. The chemical definition of a strong acid is one that dissociates completely. Hydrochloric acid satisfies. Right? In aqueous solution, that molecule 100% produces hydrogen ions and chloride ions. There's none of this left. That's a very strong acid in chemical terms. But what if the concentration we were comparing concentrations? Say we have 10 molar hydrochloric acid, and it produces, consequently, 10 molar hydrogen ions. That would be extremely dangerous. But what if we had 0.001 molar hydrochloric acid? It would produce 0.001 molar hydrogen ions and be virtually safe. You could probably drink it and it wouldn't hurt you. But HCl in aqueous solution is still a strong acid, whether it's high concentration or low concentration. That's what I mean by the chemical definition of a strong acid. Okay. So there it is in black and gray background. And that's what we mean. An almost total dissociation of the acid to produce protons. And in reality, those protons associate with water molecules. So, with that definition in mind, a weak acid would just be an acid that does not dissociate to any great extent. And a good example of that is acetic acid. Right? In aqueous solution would produce what? Well, it's protons plus H3O2 minus. Okay, that is a weak acid. Why? Because this is an equilibrium situation in which most of the acid is over here, right there. Okay, very little of it is over here. That's our chemical definition of a weak acid. Okay. So this is an artist's idea of difference between a strong acid and a weak acid. Now, let's go back to our discussion of whether it's hazardous or not. If this is vinegar, vinegar is 5%, let's see, mass volume solution of acetic acid. Right? It produces very little hydrogen ion, just enough to give you a tang. But suppose we're not putting vinegar on our salad. Suppose we're in a research laboratory and we're using acetic acid from a concentrated source to do some reaction. It is possible, and I've had these bottles of this stuff in my lab at 100% pure acetic acid in a bottle. It's called glacial acetic acid. That is extremely hazardous. Even though it's only slightly dissociated, right, by this reaction, since the concentration is so high, it produces large amounts of hydrogen ions. And you would not want to submerge any part of your body in that material. It would be corrosive, it would be damaging very quickly. So even though it's a weak acid, it can be hazardous. In addition to that, it's an organic compound, right? What happens to organic compounds in the presence of oxygen? Well, if there's an ignition source, they will burn, right? So this stuff is also flammable. All right. So here's a relative description of strength of an acid. Notice that if we're saying with our generic acid, that if it's a strong acid, what does it do? Well, if it's a strong acid, it wants to be like that. Most of it is over there. Okay? So if this is a strong acid, what does that say about its conjugate base? If we have a strong acid, then it prefers to be over here, which means what? What is a base by the Bronsted-Lowry definition? It's a proton acceptor. So if the proton donor is strong, then the proton acceptor will be weak. It got there because it didn't want the proton. So now our conjugate base is weak. That's what we're saying here. Based on the relative strength of the acid, if it's a very weak acid, the base that it produces is strong. Right? So if this is a weak acid, like acetic acid, then the conjugate base will be strong. In other words, it will be able to extract a proton very easily from a water molecule. That's not the only case, but an example. Okay. So for a strong acid, the forward reaction is dominant. It produces the proton and the conjugate base. For a weak acid, the reverse reaction is dominant. And the weak acid produces a strong conjugate base. Okay? Let's see. Common strong acids. We mentioned hydrochloric acid. That's definitely strong. Sulfuric acid is a strong acid. But let's think about that for a second. When we talked about the acidity of sulfuric acid, we only mentioned the first proton, right? It's got another proton. And notice for acids, you'll always have the proton comes first. The hydrogen ion comes first in the molecule. If there are other hydrogens in the molecule, then they're considered non-acidic. That is, they do not dissociate. For instance, acetic acid. This proton is acidic. It will dissociate. But these protons are locked in the organic matrix of that polyatomic ion, and they do not come loose. Okay? So that's why we write it with the protons that we're interested in are first, and then everything else. So the sulfuric acid can dissociate twice. It can produce a proton through one reaction, then it can produce the second proton. Well, as it turns out, only the reaction that releases the first proton is the strong acid. The second proton release is weak acid. It's kind of weird, unless you stop to think about it. Right? If we've got this going on, right, and it produces a proton plus HSO4 minus. Then we try to dissociate this one for its second proton. Right? Now, think about that proton. What is it trying to do? It's trying to leave a negatively charged polyatomic. Right? And it's much more difficult for that proton to remove itself from a negative charge, right? Positives and negatives attract. So it's more difficult for the second proton to leave. So this one is strong, that one's weak. Okay. Hydrochloric acid we mentioned already is a strong acid. Nitric acid is a strong acid. Perchloric acid is a very strong acid. I mean, just unbelievably strong. I used to use it to digest plant material. It's very effective. And it's not just the acidity that matters, it's that polyatomic ion is a strong oxidizing agent. And maybe we'll talk about that later when we discuss let's see, I think we're going to do that, aren't we? Yes. We're going to talk about redox reactions. So that's a teaser for the next chapter. So how do we name acids and bases? I think we did that when we were talking about nomenclature. Right? So this is a reminder. How do you name the acid? Well, it depends. Does it have oxygen in it? Right? If it has oxygen in it, you do not start the name with hydro. You just look to the second part of the molecule, the anion part, and start from there. So this HNO3, we would say, if it's not in aqueous solution, we would say hydrogen nitrate. So 8s become X when we name an acid. So put it in water, now it becomes nitric acid. Okay. Now, if there's no oxygen, then we do say hydro, like hydrochloric acid or hydrofluoric acid. Okay. Now, these acids with their protons, right? Proton there, proton there, proton there, proton there. Those acids, if they have oxygen in their makeup, which is usually the polyatomic ion that's attached to the proton. If they have oxygen there, we call them oxyacids, right? It's very original. Okay. Acids like acetic acid that have an organic structure are called organic acids. And most organic acids, not all, but one very common one, particularly in biochemistry, has the carboxyl group attached to it. This one. Like that. Then you have something else out here. Sometimes we use a placeholder. You just put an R there. So this is some organic part of the molecule, and this is where the proton comes from, right? This carbon has a double bound oxygen to it, a single, and this hydroxide. That produces the proton. Okay? So sometimes we write acetic acid, right? This is the way, and this is the way I've written it so far, C2H3O2. But if we write it with this structure in mind, right, then we have the second carbon over here. We've already used a hydrogen and both oxygens, So now we have these 3 hydrogens left over. Okay? So that would be the structure, a representation of acetic acid. It's an organic acid. There are other types of acids, like lactic acid. If you exercise really hard, then within a few hours, maybe a day, your muscles will start to get sore. They're producing lactic acid in your muscles, and it hurts. Formic acid, right? In formic acid, you have this part of the molecule, and then the R is just hydrogen. Where do we see formic acid? Well, let's see. If you've ever been bitten by a fire ant, then you know what formic acid is. In fact, the word formic or formate is derived from the Latin word for ant. Right, so when they bite, they spit that stuff into the wound and it hurts. Uric acid. Uric acid is, we're not supposed to have a lot of uric acid in our bodies. If we do, then it produces trouble in the joints. It tends to accumulate in the joints. Uric acid is typically associated with gout. But there are some animal species that produce uric acid as a way of eliminating nitrogen, waste nitrogen from their bodies. Birds and some reptiles produce uric acid and expel it as a solid. It is a solid. So when you see bird poop, right, it has 2 things in it. It has the dark matter, which is normally what you associate with feces, but it also has the white stuff in it. That's uric acid. It's eliminating nitrogen waste from its body as uric acid. Now, where is the proton? Well, let's see. There's one here. There's one there. There's one there, one there. It could be any one of those. I don't know offhand or remember offhand which one it is. Which one is preferred as the acidic hydrogen. Citric acid. Bite into a lemon. Citric acid. Right? In this case, it has 3 of these groups right here. One there, one there, one there. Each one of those produces a hydrogen ion. Dissociates to produce a hydrogen ion. And the way we write organic molecules, I didn't say this before. Whenever you have 2 lines, a line is a bond. Whenever you have 2 lines meet, at that meeting point, if there's no element given, that is a carbon. So that's a carbon, that's a carbon, 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 carbon. Okay? It's just convention, so they don't have to write carbon C's all over the place. All right. So consider a 1 molar solution of HCl. Now, when they say solution, for our purposes, we're assuming that's aqueous. It's in water. Okay, what are we going to do with it? Order the following from strongest to weakest base. Okay, now we have to think. HCl produces what? HCl produces hydrogen ions plus Cl minus. This is a strong acid, right? So this is a very weak base. All right? For comparison, we have another acid here. That's a weak acid. And it dissociates into that plus this. This is a strong base. Okay? And we also have, so we've got the A minus identified, we've got the chloride ion identified. This is going to be the weakest base, probably. This should be the strongest base, and water will probably be in the middle. But we have to think about, okay, water as a base. Bronsted-Lowry says if it's a base, it donates a proton. Accepts a proton. So how willing is water to accept a proton? Not very, but it's more willing to accept a proton than chloride is. So the order should be from strongest to weakest. The strongest base should be this one, and then water, and then chloride is the weakest. Right? Chloride's a very weak base. A minus is a very strong base, and water is sort of in the middle. So that's our order. Okay, let's compare two weak acids. Acetic acid here and hydrocyanic acid. They're both weak acids. But we can say, based upon their equilibrium constant, right, the K value, the Ka, we can say which one is stronger than the other. And it turns out that acetic acid is a stronger acid than the hydrocyanic acid, which means what? Let's see. So I'll turn this one into hydrocyanic. And then we have acetic here. All right. If acetic acid is a stronger acid than hydrocyanic, that means this one, it prefers this side of the reaction more so than this one does. So if that's the case, then the K value for this one, Ka for acetic acid, should be larger than the Ka for hydrocyanic acid. Okay? Because this one says it prefers that more, which means this is the numerator. That means the K value should be larger than this one at equilibrium. Okay, that being said, we want to order these in terms of the weakest to the strongest base. Right? So if this is a weaker acid than that one, then that means this is a stronger base. So that means this one is a stronger base than that one. Okay? But in order of strength. Well, that's, okay, I've got it backwards. This is a stronger base. So if we write it the way they want it, then it would be this one is a weaker base, weak to strong, than that. Now, what about the rest of it? Well, we know that chloride is the weakest base you can have because HCl is a strong acid. So we know that chloride has to be out here somewhere. Right? It has to be weaker. The question is, where do we put water? Now we need to understand water itself. Water, pure water, can undergo acid-base reaction. One water molecule becomes the acid, the other water molecule becomes the base. So we can transfer, if one water molecule is an acid, then it donates a proton. So this one donates a proton to that one. Now we have the conjugate base is here. We're making bases in blue and acids are in red. So the conjugate base of this acid is formed, and the conjugate acid of this base is formed. And there is an equilibrium established for that reaction. Now, at equilibrium, what is the equilibrium constant for this reaction? Well, at 25 degrees Celsius, the Kw, now we have a new subscript. The Kw is the equilibrium expression constant for that reaction. It's equal to 1 times 10 to the minus 14, extremely small, which means what? It means it doesn't produce a lot of that stuff. It produces some product, but not much. It's very, very small, much less than 1. And notice also that this is a pure liquid and that's a pure liquid. So they're not part of the expression. The only part of the expression is aqueous and aqueous. So that's why you only have these two terms, hydrogen ions, hydroxyl ions. The product is equal to 1 times 10 to the minus 14. Okay, so what does that say about water? That means water as a base is very weak, extremely weak. But it's probably stronger than this. Let's see, no, this would be a stronger base than water. But this one would probably be a weaker base than water. So I would say, let's move this one here. And let's put water in here. Maybe I'm right. I'm not sure. Maybe I'm wrong. Let's see. Okay, I was wrong. They're saying that this one is a stronger base than water. Well, I won't write it because it's right there. And it's all based upon that equilibrium expression. So if we had the equilibrium expression for each one of those, we could actually quantitatively decide which one is the stronger base, which one is the weaker acid. Okay. So there's a word that describes this reaction where water reacts with itself in an acid-base reaction. We call it amphoteric. Ampho is the Greek prefix that means both. So it acts both as an acid and a base. So here's our equilibrium expression. Hydrogen ions times hydroxyl ions equals 10 to the minus 14th. Very small number. And no matter what else we put in the water, we dissolve something in it, this reaction is still occurring. And the equilibrium constant for that reaction does not change, no matter what else we put in it. As long as the temperature stays 25 degrees Celsius, this expression is valid, and that equilibrium constant is still active. Okay. There was a chemist, I think he was Danish or Swedish. Or maybe he was, I can't remember. His name was Sorensen. And he was working with acid-base solutions. and wanted a more convenient way to express the acidity or the basicity of a solution. Instead of saying the concentration of the hydrogen ions is 1.72 times 10 to the minus 20 molar, he wanted some way to express it in more compact form. So he invented a mathematical expression. Well, first of all, if we're describing the dissociation of water, and now I'm going to simplify it. Let's just say water dissociates into protons and hydroxyls. Okay? Just like we did before, we throw out one of the waters and just use one. Then the equilibrium constant is equal to this concentration times this concentration. And that's equal to 1 times 10 to the minus 14. Okay? Now, if this is pure water, then where do these guys come from? They both came from the same water molecule. So if you have an expression here at equilibrium that gives you that value, then these have to be equal because they came from the same source. That concentration should be equal to that. So what does that mean about the concentration of hydrogen ions and hydroxyls in pure water? Well, in order to get this expression, you got to multiply this one times this one. So 10 to the minus 7 times 10 to the minus 7 will give you 10 to the minus 14. So in pure water, a condition we call neutrality, the concentration of hydrogen ions is 10 to the minus 7, concentration of hydroxyls is 10 to the minus 7. That is neutral. The concentration of both is the same. Now, I suppose theoretically, we could say if we could manage somehow to make the concentration of hydrogen ions 10 to the minus 5 and the concentration of hydroxyls 10 to the minus 5, we would have a neutral solution. The problem is, when you do that, you are shifting the equilibrium. And this constant is still active. The equilibrium will shift until you reestablish that ratio again. So no matter what we do in a neutral solution, the concentration of hydrogen ions and hydroxyls will be 10 to the minus 7. If we have more hydrogen ions than hydroxyls, then you have an acidic solution. And it will taste sour if you taste it. If the other way around, you have more hydroxyls than hydrogen ions, then you have a basic solution. Okay? But in each case, this expression must be obeyed. In aqueous solution, that one is always the case. So if you have more hydrogen ions, say we were able to establish 10 to the minus 5 molar hydrogen, what would the hydroxyl have to be to give you 10 to the minus 14? Well, it would have to be 10 to the minus 9. Right? 10 to the minus 5 times 10 to the minus 9 is 10 to the minus 14. So in aqueous solution, this expression always is always active and must be considered in any acid-base reaction. Now, sometimes you can figure from what you put into it that it's not a major contributor to the final outcome. So, for instance, if you take a liter of water and you dump 100 milliliters of concentrated hydrochloric acid into it, I don't think the water reaction, the KW for that, is going to influence the outcome very much. You overwhelm it with this strong acid. Okay. In an acidic solution, the hydrogen ion concentration should be greater than 10 to the minus 7. Okay. And 10 to the minus 5 is in the upward direction. That is more concentrated. I mean, yes, a higher concentration is 10 to the minus 5 greater than 10 to the minus 7. Okay, so I mentioned Sorensen earlier. We'll get to him eventually. Just take a minute or two. Let me see how much longer we have to go in our discussion. Not too much longer. Okay. So in an aqueous solution in which the hydroxyl ion concentration is 10 to the minus 10 molar, what's the concentration of hydrogen ions? Well, we have an equilibrium expression here, right? That's still valid. So if we have 2 times 10 to the minus 10th hydroxyls, is equal to this, and this is our unknown, what do? You solve for the unknown. Right? Just like this. We're rearranging the equation ahead of time, right? But we're still solving for the hydrogen ion concentration, and that makes it 0.5 times 10 to the minus 4 molar, or if we change it to standard scientific notation, that's 5 times 10 to the minus 5 molar. And is that greater than or less than 10 to the minus 7? Well, it's greater than 10 to the minus 7. So this solution is acidic. Okay. All right. Now we've made it to Sorensen. What Sorensen did was he said, all right, I need some way to simplify an expression of acidity and basicity. So he said, I'm going to take the concentration of hydrogen ions and I'm going to take the logarithm of it. That will simplify it to a single number. Okay? But say we're expressing this in terms of neutrality. 1 times 10 to the minus 7. So what's the common logarithm, right? Base 10. We'll scratch your head and remember how to do logarithms. Logarithm base 10 of this value is equal to minus 7. Right? The log of any power of 10 is the power. But Sorensen didn't want to mess with negative numbers either. So he said, well, it's just a mathematical expression. I'm going to do this. Take the negative log. Now we've got plus 7. And he called this little p, big H, pH. That's the expression for pH. Now, what if you know pH and you want to find out what the hydrogen ion concentration is? Well, you have to say, where did this come from? Go back to this. Right? So the logarithm would have produced a negative number. So you have to say negative 7. That takes care of the negative. Then you say, how do we resolve log base 10 of some number is equal to minus 7? You have to understand and remember how logarithms are built. This is the power of 10 that gives you that number. So x is equal to 10 to the minus 7 power. Sometimes you'll see this expression as x equals the anti-log of -7. Okay? But on your calculator, when you look up what button to push, once you've decided that this is a negative power of 10, you just look for the button that says 10 to the x power. And it's usually located close to the log key. All right. So what does that mean about acidity and basicity? If this is neutral, then what kind of scale are we looking at for a logarithmic scale expressed as pH for acid versus base and neutral? We've already established neutrality. Right? So pH here is 7, and hydrogen ion concentration is equal to 10 to the -7. Okay? So what if the concentration of hydrogen ion gets bigger? Right? 10 to the -6. Right? So we're increasing here, hydrogen ion concentration, 10 to the -6 molar. What does that do to the pH? Well, the negative log of 10 to the -6 is what? 6. So the pH is 6. What if we get bigger? Say we go down here to 10 to the -2. Right? That's a higher concentration than this one, isn't it? Well, what's the pH? The pH is 2. What if we go the other direction? A smaller concentration of hydrogen ions, 10 to the -8. Then the pH would be 8. See where this is going? If we go down here, maybe 12. 10 to the -12. Hydrogen ions. This would be pH 12. Now, what's happening to the hydroxyls while we're doing this? Well, the hydroxyl here would be 10 to the -7, right? But if we go this direction, the hydroxyl is 10 to the -8, because that one times that one has to be 10 to the -14. Down here, this will be 10 to the -12. Oh, excuse me. Yeah, 10 to the -12. Hydroxyls. On this end, we would have hydrogen ions are 10 to the -8, so this would be 10 to the -6, and then this one would be 10 to the -2 hydroxyls. So see, we're increasing hydroxyls this way, decreasing that way, and we're increasing hydrogen ions this way and decreasing that way. And the end result is the pH is smallest for the greatest acidity and largest for the lowest acidity. So this side is acidic and this side is basic. All right. A word about significant figures. This is an artifact of logarithms. So just memorize it. Significant figures. If you take the log of a number with, let's say, 1.076 times 10 to the -3. This is hydrogen ion concentration. Okay? If you take the negative log of that number, let's just do it. I just made this up all of a sudden. 1.076 10 to the -3 Okay, take the log of it and then the negative of that. Change the sign. So I get if I keep all my decimals, I get that number. Okay, how many of these figures are we allowed to keep? Well, the rule is the number of decimal places in the log here is equal to the number of significant figures in the original number. So if we've got 4 here, significant figures, we can keep 4 decimal places here. Okay. So I need to round this to a 2. There you go. So this is the pH of that number with the proper significant figures retained. Now, if you go backwards, if you take the anti-log of this number, or the negative, the 10 to the negative, that number, then you get to keep 4 significant figures because you have 4 decimal places. Okay? That's the rule. Okay, before I erase that, let me see if there's anything else here I need. All right, there's your pH range. That's everything I just described on the board. These are some examples. Right? Stomach acid is between 2 and 1 pH. So it's corrosive. And it's primarily due to hydrochloric acid. That's what your stomach produces to start digesting food. Well, actually, some digestion takes place in the mouth with your saliva. You got amylase is an enzyme that we produce in our salivary glands, and it starts breaking down starch. That's why if you put starchy food in your mouth and keep it there for a little while, it tastes sweet because you're breaking that starch down into simple sugars. Anyway, vinegar is about a pH 3.1 or 2. Lemon juice is worse than that. Milk is slightly acidic. Blood is slightly basic, right? If you've had any anatomy and physiology classes, you know that the pH range of normal, healthy blood it's very narrow. It's like, if I remember correctly, let's see, 7.35 to 7.45, I believe. Right. Check with your physiology instructor and see if I'm right here. But anything below that or above that, you start to feel sick. And if you go way far up from those values, either way, then you could cause coma or death. That's one of the main issues with diabetics, because a diabetic that goes into ketoacidic shock is doing something bad to their blood. They're making it more acidic. Okay. So what's the pH for each one of these? Okay. I'm out of time, but I'm going to keep talking. So this one should be fairly easy because your coefficient here is 1. You only have to focus on the power of 10. So what's the negative log of this value? Would be 4. So the pH of this solution is 4. So it is acidic. How about this one? How do you do the pH of that one? Well, one way is to use your equilibrium expression and find out what is the hydrogen ion concentration if you use hydrogen ions times hydroxyls equals 10 to the minus 14, your Kw. If you do that, then you find that the hydrogen ion concentration is this value. And then you take the negative log of that value, and you find that the pH is 12.6. So this solution is basic, right? pH is greater than 7. It's a basic solution. This is going backwards. If you have the pH of 5.85, you can determine what is the hydrogen ion concentration. Sometimes you need to do that for the sake of calculating something else in your problem solution. So there's 10 to the minus 5.8 gives you 1.41 times 10 to the minus 6. Now, did we do this right? 3 significant figures, but you only have 2 decimal places. Okay, so that's an error. That should be 1.4 times 10 to the minus 6 because you only have 2 decimal places in your pH. All right. Here, the concept to hang on to for the next discussion is that the calculation of pH is simply a mathematical expression, right? It has no significance, no added significance in chemical terms than the pure expression of a mathematical calculation. So we could do the same thing to hydroxyl concentrations. We could say POH instead of pH and do that negative log calculation of the hydroxyl ion concentration. Perfectly valid. So if I were to do that, if I were to take the hydroxyl ion concentration and take the negative log of that value, I will get POH. Correct? We can go even one step further. What if you know the KW? Take the negative log of that. What is that going to give you? Well, we take this part and put a P in front of it. pKW. It's just a mathematical operation. So if we have this expression where KW equals hydrogen ion concentration times hydroxyl ion concentration, we know that we can do the conversion now to P expression. Why not do the whole thing to that equation and see what we get? Okay. Negative log of KW, we know where that one's going, pKW. The negative log of this expression is what? There's a rule in logarithmic calculations. If you take the log of a product, A times B, that's the same thing as saying the log of A plus the log of B. Okay, so that's what we're going to do here. We take the negative log of this plus the negative log of OH. Now we have pH plus POH equals pKW. And what is pKW? The value of pKW. We'll take the negative log of what it is. The negative log of 10 to the minus 14 is what? It's 14. Okay? So that whole discussion was designed to prove that you can do this. 14 equals pH plus POH, which in turn is equal to pKW. Now we have a simpler way to determine the pH of a solution if we only know the POH. If we know the hydroxyl ion concentration, we can calculate the POH, subtract it from 14, and get pH. That's a much simpler operation than the way we did it before. So in this case, that's still true. pH is 4 for this concentration. But for this one, we want to take the negative log of that value and then subtract it from 14. Oh, excuse me. I read my own questions. We want to calculate the pOH. So if we know the pH is 4, then we subtract 4 from 14 and we get the pOH of this solution is 10. 10 plus 4 is 14. For this one, we calculate the pOH is 1.40. What's the pH? Subtract 1.4 from 14, we get 12.6. If the pH of a solution is 5.85, oh, excuse me. What's the hydroxyl ion concentration? Well, if we subtract 5.85 from 14, we'll get the pOH, and then we take the anti-log of negative of that value, and we get the hydroxyl ion concentration. Okay. So pOH is 8.15, so 10 to the minus 8.15 is equal to our hydroxyl ion concentration, and there it is. So if you need to know the hydroxyl ion concentration for a calculation, and you only know the pH, there it is. So how do we calculate the pH of a strong acid? In order to do that, it's actually very simple. By definition, a strong acid completely dissociates in aqueous solution. So if you know the concentration of your acid when you put it in solution, you will know the concentration of hydrogen ions in that solution. So in this case, if it's 2 molar HCl, then the hydrogen ions are going to be 2 molar, and the pH is going to be minus 0.30. Did you ever think you'd get a negative pH out of this? Well, it's just a mathematical operation. You know, anything's possible. But Sorensen was interested in pHs that were between about 1 and 12. He wasn't interested in negatives. But that doesn't mean you can't calculate. Okay. All right. So what's the pH of this solution? 2 times 10 to the minus 3 molar. Well, we know that the hydrogen ion concentrations are going to be equal to the acid concentration because it's a strong acid. So if we take that value and do the negative log conversion, we find that the pH is 2.7. Now, you may be thinking, and I hope you are actually, that, you know, where's water in all of this? Well, water is a very weak acid. So when you have this much strong acid in solution, the contribution of water to the final pH is negligible. Only when you get down to very, very low concentrations of the strong acid do you need to consider the influence of water dissociation as an acid. And that really, well, this is an illustration of that fact, right? If you put hydrochloric acid in solution at this concentration, what's the pH? Well, look, first, the relative concentrations, if it's pure water, the hydrogen ions are going to be 10 to the minus 7th molar. If hydrochloric acid is put in there at 10 to the minus 11th, that's 4 orders of magnitude weaker in concentration of hydrogen ions. They will have no impact whatsoever on the pH. The pH is still 7. Okay? So that's why we can say the pH is 7. Even though we put this strong acid in there, we only put it at that concentration. It has no impact on the solution pH. Okay. Here's another example. We're just using nitric acid this time. You have to recognize, do you have a strong acid? Then you can do this calculation. pH 1.82. And notice the difference between this concentration and the concentration of hydrogen ions in neutral water, 10 to the minus 7. That's 5 orders of magnitude stronger in absolute amounts of hydrogen ions. So we don't need to consider the equilibrium of water molecules as a contributor to the final calculation. Okay, what do we mean by a buffered solution? This is our last concept of the day. In chemical terms, a buffer is one that resists the change in pH when you add acid or base to it. So once we have a buffered solution, then anything we do to it will change the pH slightly, but not very much. If it's an unbuffered solution, like pure water, then when you add acid to it in sufficient amounts, you will change the pH dramatically. But with a buffered solution, when you add acid to it, the buffering chemistry in there absorbs some of that hydrogen ion. And that means that the pH does not change very much. But you can also add base to it. And the chemistry will also convert that OH minus into usually water. Okay. So how do we make a buffer? Most buffers are made by the combination of a weak acid and its conjugate base. So if we prepare a solution with some of this and some of that as a separate addition, then we can theoretically produce a buffered solution. But it has to be a weak acid. Strong acids don't work. Why? Because a strong acid produces all of this and none of that is left. So there's no give and take. So what happens to the solution if this is a buffered, if this is part of our buffering system? This is the balanced equation for our buffered solution. What happens? Let's see, I already said that. What happens if we add acid to this system? It's at equilibrium now. If we add acid to it, what's it going to react with? Well, if this is a weak acid, that is a strong base. And what we mean by a strong base is it is very aggressive at attaching itself to protons. So this very aggressively attaches itself to that proton. And what does that make? That makes some weak acid. Right? So we've added acid, but we've also consumed it and driven the reaction back this way. Its equilibrium position now has changed. The equilibrium constant didn't change, but the position did change. And we used up some of these hydrogens. But since this is equilibrium, We didn't use all of them. We used a large portion of them to reestablish equilibrium. So that's why we say a buffered solution does not fix the pH. It resists a change in pH. So we'll still get a slight change in pH, but not a big one. And when you add acid, that's what happens to it. What happens when you add hydroxyl? When you add hydroxyl, instead of reacting with this one, it reacts with the hydrogen ions and produces water. Okay? Remember the equilibrium expression for water, hydrogen ions, and hydroxyls? Where does this reaction want to be? It's a weak acid. It wants to be here. So when you present it with hydroxyls and hydrogen ions, it wants to be there. So it consumes these hydrogen ions, produces water, and now you've removed a large portion of the hydroxyl from solution as well. So it doesn't matter whether you add hydrogen or hydroxyls. One or the other is going to be absorbed into that reaction and stabilize your pH near a certain point. It'll drift a little bit depending on what you add, but not much. Okay. Okay, this one is a little bit different, right? The example that I gave you before was a weak acid combined with its conjugate base, a strong base. In this case, we have a weak base combined with its conjugate acid. So let's see what happens there. So here's what we've got. Ammonia is in equilibrium with that. Okay? Or actually, let's be more accurate. Let's be truthful here. Ammonia plus water yields ammonium plus hydroxyls. Okay? Now, where does this reaction want to be? On this side. It's a weak base, proton acceptor, a weak proton acceptor. So this is a weak base, and this is a strong acid. Okay? Let's see, is that right? This is a weak base and that's a strong acid. Then this would be, well, this is a weak acid, which makes this a strong base. Okay, there's nothing wrong with that. That works. Okay. So a strong acid wants to give up its proton and a strong base wants to take it. So they're perfectly happy to exchange that proton, and this is where it wants to be over here. There's very little of that. Okay, now that we've got that established, let's see. What reaction will occur if a strong base such as sodium hydroxide is added? Okay. We didn't mention strong bases, but the same concept holds for strong bases as well as strong acids. A strong base completely dissociates into the cation plus hydroxyls. So what's produced? Well, sodium ions, they don't react with anybody. They're spectators. So we've produced hydroxyls from the addition of the strong base. Right? So we're going to increase this amount. What is it going to do? It's going to react with that strong acid. It's going to take a proton from here and drive the reaction backwards to there. So we've consumed some added hydroxyls. That means instead of making the solution more and more basic, make it only a little more basic. Okay, so this one picks up that hydroxyl and transfers that hydrogen ion to the hydroxyl and makes water. So this hydrogen ion plus that one produces water, and then what's left over is that weak base. Okay? Well, that's it for our discussion. Introduction of the material. So now go to Blackboard and find your review document and work some of these problems. Get some practice working those problems. And next, let's see, this is Tuesday, Thursday, we'll review that those problems in the review document. And that'll set you up for an exam on next week, next Tuesday, I believe.